Welcome to video 28. We're going to talk about the forces between charges using Coulombs law, but I thought I'd jump right to the case with more than one charge. When you only have two charges, the direction is really easy. When you have more than two charges, you've got to take the direction into consideration. So in a lot of ways, this becomes a vector problem, and most of the time you haven't done vectors in quite some time when you get to this. So let's draw a picture that helps. It doesn't have to be to scale necessarily, but I've got the graph paper, so I thought I'd use it. We've got three charges, so these positions are going to be, well, let me draw C first. So let's make this 0. So 1, 2, 3, 0. That's going to be charge C. And at 0, 4, 1, 2, 3, 4, that's going to be charge A. And 6 over from there, we've got charge B, and these are all exerting forces on one another, but we're concerned with the forces acting on particle C. So A, just so we have it, has a Q that is going to be plus 3 microcoulombs. B is minus 1 microcoulombs. And C, the charge in question that we're finding the force of, has a charge of plus 2 microcoulombs. Now that may not sound like a lot of charge, but that's actually a pretty good amount of charge. And we don't know what these forces are going to be, but if you look, this one up here is negative. This one down here is positive. So negative is going to attract positive. It's going to be up in this direction. So if I was to draw an arrow, it would go sort of like this, with a magnitude to be determined by the size of the forces. Similarly, from A, that's going to push it away. Positive is going to repel, and it's going to be along a direction like this. And we need to consider two things. We need to look at the magnitude of the forces, and we also need to look at the directions. So let's just take a minute and try to determine the directions. And the way I encourage you to do that is to actually break it out somewhere on the side. So if you're looking at this, you can see you go over 3, down 4. So this is almost like when you did vectors. Over 3, down 4. So this is 4, this is 3, and we're trying to get, I have colors, I may as well use them. We're trying to figure out what this direction is. So what's this theta? The angle in the bow tie, if you will, of the overall direction. What's a special triangle? 3, 4. Some of you, I can see at home, are already screaming, you know the answer, it's 5. It is 5. But do you remember what this theta is? If you don't remember, and that's okay, you can see that this is an opposite side and this is an adjacent side of this. So that's going to be 4 over 3, and when you take the inverse tangent of that, that's going to give you a theta that is 53.1 degrees away from the positive x-axis for this one. So we've got a direction, we've got a magnitude in terms of distance. That'll be important when we do Coulombs law. And if you look at this vector, you can see I made it symmetrical, but if we were to go ahead and draw that, it would basically just go up 4, 1, 2. So from here, 1, 2, 3, 4, and over here, 1, 2, 3. And you can see you're going to go up 4 over 3. And that's going to give you a magnitude, again, that is 5. You got to be really careful when you get the direction, because you want to measure the direction relative to the x-axis. So again, the opposite side is going to be 4. The adjacent side is going to be 3. And that's going to give you this theta is also going to be 53.1 degrees. And that just comes out of the symmetry of the problem. So we've got directions and we've got the distance. The other thing to remember here is that this is going to be in the positive x direction, and this is going to be in the positive x direction as well, but this is going to be in the positive y, whereas this is in the the negative y. Now let's give names to these forces. Since this is C and this is B, we'll call it the force from B acting on C, and we'll call this the force of A acting on C. And we're going to be adding these vectors, but let's figure out what their magnitude is first. So Coulomb's law tells us that the force between any two charges is going to be equal to a constant K times Q1, which is charge 1, Q2, which is charge 2, over R squared, which is the distance between those two charges. So we're going to consider them one at a time. So if I was to figure out the magnitude of the force between charge A and charge C, and let's just worry about the magnitude. Let's not be too concerned with the sign. K is about 9 times 10 to the 9th newtons meters squared per coulomb squared. Remember, if you want to get a force, the bottom is coulomb squared to cancel out with the charge squared, and the meter squared cancels out with the distance squared, which gives you just newtons, which is what you want. You want a force. So that's going to be the K. Q1, or QA I should say, is going to be 3. And this is where you got to be a little careful with the prefixes. The mu C, that's going to be 3 times 10 to the negative 6 coulombs, and the times negative 6 definitely matters. And then charge C is also plus, and that's plus 2 times 10 to the negative 6 coulombs. And the distance between them, remember we found that over here. This happened to be a special triangle, so 3, 4, 5. The distance between A and C is 5, but that's 5 centimeters, so that's going to be in meters. Again, you've got to be really careful with your units here. To cancel out this meters, these have to be in meters. 0.05 meters squared. And when you plug all that into your calculator, you should get a force with a magnitude of 21.6 newtons. And we've already seen that it's going to act in a direction that is going to be 53.1 degrees below the positive axis. But we'll hold on to that. Similarly, you can get a force between B and C, and that's going to be the same constant, 9 times 10 to the 9th newtons meters squared over coulomb squared. That's the K. The charges are going to be just a little bit different in that we're looking between B, which has a charge of minus 1 times 10 to the negative 6 coulombs, times, again, charge C is going to be 2 times 10 to the negative 6 coulombs, over, happens to be the same distance, isn't always that way, but in this problem it is, 0.05 meters squared is going to equal. Now for those of you that are really good, you can see the only difference between this and this is 2 times 3 is 6, and negative 1 times 2 is negative 2, so you'd expect it to be negative a third of that, and it is. Negative 7.2 newtons. And all the negative means is that they're going to be attracted to one another. So this negative charge and this positive charge are attracted, which is exactly what we would expect. From this point on, it's really just a vector problem. But it's been a while since most people have had to do vectors, so let me just remind you. Here's the way I like to do it. It's important to consider the x and y components separately. So across the top, I like to have x and y, make those nice and separate. We've got a force between charge A and B, and another force between charge B and C. To get the components, look at the diagram. No matter what we get for AB, we don't know what it is, but we know that it's going to be, hold on, let me pause this. Sorry, I just misspoke a second ago. The force between BC is going to have a positive x and a positive y, and the force between A and C is going to have a negative y and a positive x. So let's go ahead and write those in. X is going to be between A and C and B and C. Between A and C, you're going to have plus x minus y. So that's going to be plus and minus. Whereas between B and C, it's going to be plus y and plus x. Remember, if we're going to get the x component, that's the magnitude. In the case of AC, that was 21.6 newtons times the cosine of 53.1 degrees. And the y is going to be 21.6 times the sine of 53.1 degrees. And B is going to be similar. It's going to be 7.2 newtons times the cosine of 53.1 degrees. And this is going to be 7.2 newtons times the sine 53.1 degrees. And then what you want to do is you want to add these x components up, put those here, add these y components, put this there. Now, I may be boring you, but there's a fast forward button, so let me go ahead and write these in the chart. Again, FAC, force between B and C. When you put this in your calculator, you should get 12.97 newtons. This is a public service announcement. If you're not getting this number, there's a real good chance that your calculator is actually in radian mode, so you want to double check that. Type in sine of 30. If you're not getting a half, you're not in radian mode, or you don't know how to use your calculator. And for B, 7.2 times cosine of 53.1 gives you 4.32. And then when we look at the y components, this should give you negative, remember, because it's down, and 5.76 newtons. And when I add those up, I get 17.29 for the x component of the net force, and for the y component I get negative 11.51 newtons. And now we just need to get a magnitude and a direction from this. So I like to sketch this, and it's going to have an x component to the right of 17.29 newtons, and it's going to have a y component somewhat smaller. Actually, I usually don't write the negative sign when I draw the arrow because it's a little redundant. Like this. And now to get the resultant, let's use green. Like this, to get the magnitude, use Pythagorean theorem, which tells us that the magnitude of F net is going to be the same as 17.29 squared plus 11.51 squared. Take the square root. I cheated and did this ahead of time. It's not really cheating. It's just not boring you any more than I need to, and I got 20.8 newtons, but that's just the magnitude. Again, force is a vector quantity, which means you need both the magnitude and the direction. So we know it's going to be sort of off towards the right, and it's going to have a magnitude of 20.8 newtons. Now we need to figure out the direction. Well, it's going down, and to get this theta, much like before, you can see this is the opposite side, this is the adjacent side, so the theta is going to be the inverse tangent of the opposite side, 11.51, over the adjacent side. That's what they call it. And that's going to give you a theta that is 33.7 degrees. Now, there's different ways of quoting this. Some people like to say 33.7 below the positive x-axis. Some say south of east. You could give an overall direction. That's usually what I do the math way. So that would be 360 degrees minus 33.7 degrees, which gives you 326.3 degrees is the overall direction. So your final answer for the net force would be a 20.8 Newton vector in the 326.3 degree direction. So let's zoom out and look at the big picture, so to speak. Here we have 3 charges, and we're trying to figure out the forces acting on the third charge, charge C, from the other 2. Step number 1 is to figure out the distance between C and A and C and B, and to figure out the direction. Step number 2 is to use Coulomb's law for each of those 2 interactions, AC and BC, get the magnitude of the force. Step number 3 is to set up a table, X and Y components, forces, and get the X component and the Y component of each. Next, you would add those up to get the X component and the Y component of the resultant, the net force. And then finally, from those components, you would get the direction and the magnitude using Pythagorean theorem and the inverse tangent. I hope that you've found this useful, and if not, I hope you didn't watch the whole thing.